Hi, my name is Priyanka Ananiakara, and today I'm going to present our work on visualizing privacy-utility trade-offs in differentially private data releases. In this work, we designed, built, and evaluated an interactive visualization interface for data curators making privacy budget decisions in a differential privacy context. To begin, let's say there's a data curator at a hospital who's looking to publicly release some aggregate statistics about the hospital's patient data. Specifically, they plan to release rates of hypertension for subgroups according to ethnicity, age group, race, and zip code. So for ethnicity, this means releasing the proportion of people in the database who are Hispanic or Latino who are diagnosed with hypertension, and the same proportion for people in the database who are not Hispanic or Latino. The data curator also knows that the released statistics will likely be used to make inferences about a larger population. So they want to also release confidence intervals for the population proportions. They don't want to inadvertently release statistics, however, that compromise patient privacy. In other words, it should be difficult for a future viewer of the released statistics to use these statistics to figure out information about individual patients, like who specifically was diagnosed with hypertension. For this reason, the data curator decides to use differential privacy in releasing the statistics. They quickly encounter several challenges, which will be made more clear after we look at the definition of differential privacy. If an analysis is conducted under differential privacy, or DP, then we expect roughly similar outputs whether or not any given individual's information is included in the analysis. The strength of privacy protection is determined by the privacy budget, which we see as epsilon in the definition. Epsilon is a knob that can be tuned to different levels of privacy protection. In practice, oftentimes mechanisms satisfy differential privacy by adding a calibrated amount of random noise to the underlying statistic. The amount of added noise is controlled by the privacy budget. The data curator must choose an appropriate value for the privacy budget. However, there's no formal guidance for this task, which makes it especially challenging. For starters, in order to find an appropriate balance between utility and privacy, the data curator needs to keep track of probabilistic relationships between epsilon, utility, and privacy. Moreover, when considering utility, they also need to keep in mind how a given privacy budget will impact confidence intervals that can be released. And because the data curator is making multiple queries to the database, they might also need to split a total privacy budget among queries. The same privacy budget applied to different queries could have different utility implications, further complicating this task of setting a privacy budget. Those were some of the challenges we kept in mind when designing our interactive visualization interface for data curators setting privacy budgets. More specifically, we had 4 design goals. For design goals 1 and 2, we wanted the interface to help a data curator understand relationships between epsilon, utility, and privacy. For the 3rd design goal, we wanted the interface to help a data curator understand statistical inference under DP, especially how sampling error and DP noise combine in confidence intervals constructed under DP. And 4th, we wanted the interface to help in the budget splitting task. We felt that if an interface could achieve these goals, the data curator could make more informed privacy budget decisions that take into account their domain knowledge about weighing privacy and utility in a particular context. Our interface is called Visualizing Privacy, or VIP for short. Before we walk through VIP, we'll go through where VIP sits within the larger data sharing context. The data curator makes queries to VIP and sets the privacy budget. VIP then accesses the private data from the data provider, in our case that's the hospital, and VIP then visualizes the privacy utility trade-off under the set privacy budget. The data curator can iteratively choose different values for the privacy budget and see the resulting privacy utility trade-off to make a decision about what an appropriate privacy budget is in their context. Once the data curator decides on a privacy budget for each query, VIP calculates privacy-preserving results that can be made available to the public, shown here in the diagram as the data consumer. Now we'll walk through a demo of VIP and how the data curator might use it to set privacy budgets. Here we see queries about rates of hypertension across subgroups by ethnicity, age, race, and zip code. Note that each panel on the left is labeled with the query name. The Privacy Use panel on the upper right-hand corner allows the data curator to set privacy budgets for each query. There's a slider for each query, and changing the value on the slider changes the privacy budget applied to that particular query. The data curator can also use this panel to set a total privacy budget. Then, as they set privacy budgets for each query, the remaining budget updates to show them how much of the total budget is left. On the left, there are panels depicting the expected accuracy of each release. To better see what's going on in one of these panels, we'll expand the panel for the ethnicity query. We see expected accuracy for each subgroup, Hispanic or Latino and not Hispanic or Latino. The static black lines show the proportions for each subgroup with no DP noise added. The animated red lines, or hypothetical outcome plots, show potential privacy-preserving releases under the privacy budget set by the data curator. These are draws from the DP output distributions. Hypothetical outcome plots make clear to the data curator the probabilistic nature of making releases under DP. Under the hypothetical outcome plots, we show quantile dot plots, discretized versions of the DP output distributions. Since there are 25 dots in each dot plot, each dot represents roughly 4% chance. The data curator can count up the number of dots in a given range and multiply by 4 to figure out the chance that a privacy-preserving release will fall in that range. As the data curator changes the privacy budget applied to this query, both the hypothetical outcome plots and quantile dot plots update. This is also shown in the box on the lower right-hand corner. The data curator is also interested in releasing confidence intervals. The static gray bars represent 50, 80, and 95% traditional confidence intervals with no DP noise added. The animated blue bars are hypothetical 50, 80, and 95% confidence intervals calculated under DP. Showing both sets of confidence intervals allows the data curator to see how much DP noise impacts the privacy-preserving confidence intervals. On the lower right-hand corner, we show a graph with disclosure risk and epsilon. On the curve, there is a dot corresponding to each query. As the data curator updates the privacy budget applied to a query, the query's dot on the disclosure risk curve also updates. The attack model under which this disclosure risk is calculated assumes an adversary has access to all records in the database and is trying to guess whether a record was included in the analysis based on a sensitive attribute. The curve shows an upper bound on the probability that the adversary guesses inclusion in the analysis correctly for each query. To evaluate the effectiveness of VIP, we conducted a controlled user study with 16 participants. All participants had experience analyzing private or sensitive data, but none had any DP expertise. We asked participants to complete a set of tasks with both a spreadsheet and VIP. We counterbalanced the order of tasks and the spreadsheet in VIP. We designed the spreadsheet to mimic the types of information data curators might currently have when making releases under DP. For example, participants could set the privacy budget, and the spreadsheet would update the maximum distance the privacy-preserving release would be from the query result 95% of the time. The study's results showed that VIP helped participants more correctly answer CDF judgment and confidence interval comparison questions. We also found some evidence that VIP may help with the budget splitting task. Let's go through examples of these 3 task types. Details on the other tasks are in our paper. CDF judgment tasks asked participants for the probability that a privacy-preserving release would fall into a particular range at a given privacy budget. To answer this question, participants used the quantile dot plot to make quick calculations. For the confidence interval comparison task, we asked participants to estimate how many times wider a privacy-preserving confidence interval would be compared to a traditional confidence interval. Using VIP, participants could compare the widths of the animated confidence intervals constructed under DP and the static gray traditional confidence intervals. The budget splitting task asked participants to split a total privacy budget while satisfying a set of accuracy and disclosure risk requirements. For this task, participants had to rely on both the accuracy visualizations and the disclosure risk visualization. Through our user study, we found that VIP may help practitioners understand DP by helping them keep track of relationships between epsilon, accuracy, and privacy, and may also help them make relevant calculations. Looking forward, we're interested in integrating context-appropriate information into VIP. For instance, this might mean showing anchor points on the privacy budget sliders. So this might mean saying something like, in the past, your organization has released a similar aggregate statistic under this privacy budget. We also think it would be useful to create normative frameworks for evaluating DP interfaces moving forward. Thank you so much for your time. We're looking forward to hearing any questions or comments you have about this work, and we can be reached online.